So thank you for giving me the opportunity to talk. Good morning. So I'm going to be talking about analyzing and searching unstructured medical data. But just to set the scene and to highlight the difference, I'm going to give a brief example at the beginning of analyzing structured medical data. So this is some work that was done by a colleague. So he got hold of data from the Austrian Social Security. So for 2 years, he basically got a comma-separated value file, where on every line in this file, there is information about every paid health service in Austria in those 2 years. So in every line, well-defined, there is the date, there is the patient ID, so anonymized, which doctor or hospital was it, where is this, what was the diagnosis, what was the side diagnosis, which medication was prescribed, which pharmacy did he get the medication from, which date, and so on. So a nice data set. And what they did with it, they wanted to see, for example, what are comorbidities? So what are diseases that people very often have together? So you might find, for example, that people who have diabetes also very often have Alzheimer's. But there's not such a high correlation between people with diabetes and brain tumors, for example. And from this data set, from just 2 years of information, it was possible to get very detailed information. And that's what you see over there. So on the left here, you see the co-occurrence by age of diabetes type 1 and diabetes type 2, with all of those diseases listed along the right there. So you can see, for example, that there's a very high correlation between both diabetes type 1 and type 2 with the retinal disorders. That's the dark red. You can also see, for example, if you move down to the bottom here, that even though the correlation between diabetes and chronic ischemic heart disease is lower, there is actually, for males, which you see by the blue over here, a much higher correlation. So this is useful information that's being got out of the structured data, which can be used to make decisions for steering the medical social security system. But that's it for structured data. What I'm going to do now is move on to the main topic, which is unstructured text data. And I'm going to start off with an example showing the usefulness of being able to analyze the unstructured text data. So this has to do with medication. Now, before medication comes onto the market, of course, it has to undergo a clinical trial. So this means that for a certain number of people, maybe a few thousand, over a year or two, it's tested to see if it really does what it says it does, if it's better than a placebo, and also that there are no really bad side effects. But still, even though this is done, it's only done on a small number of people for a short amount of time. So not everything that could potentially happen is found then. So that means that if you're taking a medication that's just recently come onto the market, you're still part of the experiment. They're still watching you to see if there are any other side effects that come up, for example. And in the early 2000s, there was quite a bad case of an undetected side effect. That was with the medication Vioxx. So this is a medication for pain caused by rheumatoid arthritis. And it had a rather nasty side effect that hadn't been discovered in the clinical trials. And that was that people taking this tended to also have heart attacks and die. But this came onto the market. It was on the market for 5 years until in around 2004, at a hospital group in the US, some researchers decided to look into the correlation of Vioxx and various side effects. So they took medical records for 1.4 million patients and analyzed them and discovered this rather disturbing correlation between Vioxx and heart attacks. So immediately after it was discovered, the drug was pretty much taken off the market. But they actually analyzed the structured data. So with the medical records in the hospital, there are what are called codes associated with them, so ICD-9 codes at that stage. So that's what ICD-9 codes look like. Those are the various different types of heart attacks and the codes that would be associated with them. Now, in general, in hospitals, these codes are added manually. So either the doctors or nurses are expected to do this, often they don't. Otherwise, there are people who are called coders, and they need to read the text that the doctors wrote and associate these codes. But these people have a limited amount of time. So they have generally been instructed to only add the codes which are important for billing purposes, and not to worry so much about other codes that might be useful for, let's say, detecting side effects or whatever. So there's very often missing data from this manually coded information. So a few years later, in 2012, another group of researchers decided to see if it would have been possible to detect this really bad Vioxx side effect with a smaller number of patients. So they took from one hospital 14,000 patient records. The difference was that they analyzed the free text, so the text that had been written by the doctors during the consultations, and they did discover a statistically significant correlation. Not if they'd taken the ICD-9 codes, but with the free text, yes. So if it was possible to discover this with only 14,000 patients, it would have been possible to take the drug off the market much earlier. So this is an advantage of treating the unstructured information, so the free text. And this is something that we've been doing since 2010. So I've been leading an EU-funded project since 2010. The project dealt with analysis of medical text and image data, and then recently there's been a follow-up project which is still going on called K-Connect, which is focusing on the text data. So this is one sentence from an anonymized electronic medical record. And to analyze this, to get useful information out of this, the first thing that has to be done is to get the medical terms. So you can see the medical terms, and they would be cold, paracetamol, and OD. So that's the first step. The next step is to actually work out what these terms are about. So there's some there that are quite clear. It's clear that paracetamol is a very specific type of medication. But then for others, it's a bit more complex. So there's a cold up there. So either this could be a low temperature, or it could be rhinovirus. There's a very slight difference. So if Mr. ZZZ had complained of cold, it would have been low temperature. If he complained of a cold, it would have been a rhinovirus. So you need to look at the context. And then right at the end, there's this abbreviation. Abbreviations are used incredibly often in electronic medical records, and they're very difficult to interpret. So in this case, OD could be oral daily, doctor of optometry, or familial osteochondritis dissecans. And you need again to look at the context to work out what it's most likely for. So the difficult thing about abbreviations is in different hospitals, they tend to use different systems of abbreviations. Even sometimes within the same hospital, different departments use different systems of abbreviations, and the same abbreviations for different things. So that's a challenge. So within the K-Connect project, we have a partner that's the South London and Maudsley Hospital. It's a psychiatric hospital, and they're actually very advanced in transferring, as a matter of routine, their medical records for use in research. They have a pipeline that anonymizes them and puts them into a database for research use. And they can do many useful things there. So one of the projects that's currently running is they're looking at detecting antipsychotic polypharmacy. So this is for psychiatric patients. Polypharmacy is when more than one medication is prescribed. So for this, they're using both the unstructured and the structured data. The unstructured is useful because very often the doctors, for example, forget to write in the field for prescribed medicine what they actually prescribed. It's just somewhere in the text. So they're using both of these, and they're using this to find, let's say, patterns of prescription for multiple drugs for one person, or what are the effects of prescribing multiple drugs on the outcome of the disease. So again, a very useful use of the data. But this is just in one hospital. So if you think of the challenge now, let's say we wanted to do polypharmacy for psychiatric patients throughout Europe. Then we'd have to get medical records from multiple countries. They would all be written in different languages, and we would need something that can analyze all of those to get a group of people that you could then look at in more detail for the effects of the multiple drugs. So this multilinguality is one of the aspects that the K-Connect project is focusing on. So basically it's developing services for information extraction, semantic search, and machine translation. You can try them out. So there's a website, the K-Connect Cloud Market, called cloud.kconnect.eu, where those services are available for you to try out. Okay, so that was the unstructured medical text information. Now we're going to move also to include image information. So here I'm thinking of mostly, for this talk, radiology information. And there is a lot of it. So there was an estimate in 2010 that medical imaging data occupies 30% of world storage. So there's plenty of data there to analyze. So also one of the follow-ups to the Cresmoy project was a spin-off. So it's a startup, very recent, called ContextFlow, which is developing the technology for medical image search. And for that, we are, of course, working with radiologists. So radiologists tend to spend the day sitting in a sort of slightly darkened room with a screen in front of them. They get sent images from CT or MR scanners, and their job is to look at the image, scan through it, and find out if there's anything strange in there, any pathology, and then say what this pathology is. So the images they look at are, of course, today pretty much all 3D. So there's a 3D CT image. So a radiologist will sit in front of that and scroll backwards and forwards, go through the whole image, and try and find something there that looks strange. In the best case, if the radiologist does identify something that looks strange, he or she will know what it is from experience and can then basically say, okay, I recognize that, and then write a report, and that's the end of it. What gets tricky is if the radiologist sees something that looks strange but doesn't know what it is, because then you go into this loop off on the right here. So the first thing they usually do is ask a colleague. So is there a colleague around? Does the colleague know what this is? Maybe there's no colleague, maybe the colleague doesn't know. Okay, what's the next step? Well, they're looking at this thing on the image, and they need to convert it, describe it in text, so they can put it into a search engine, and hopefully some images will come back that look like what they have on their image. Also inefficient. If that doesn't work, then they have big books, and they then open up the books and they page through, and they try and match what they see on the image to what's on the screen. This is inefficient. It takes 20 minutes, for example, to find it, if they manage to find what they're looking for. Often they don't find what they're looking for. So at ContextFlow, what we're doing is actually trying to eliminate that inefficient loop on the right by allowing the radiologist to simply mark in the image what looks strange. So, for example, you see the red block over there. The radiologist simply says, okay, that's a strange-looking thing. I don't know what it is, and marks it, and clicks on search. And the system then goes off, and it brings back all relevant information that could help the radiologist in making the diagnosis for that strange-looking pathology or strange-looking structure. So the first thing the system does, it goes to the hospital archives. It does a visual comparison of what the radiologist marked over there with all of the images in the hospital archives, and comes up with, like a search engine, a ranked list of the images with the most similar structure to what was marked. And this means, like a search engine, the radiologist can click on each of those and gets information, so anonymized information with the image to look at. Also a radiology report, so that the radiologist can get information about what colleagues have written and also read what's in there. But it's not only a search engine. It also takes the reports that come with all of these images and does a text analysis of them. So it extracts anatomy and pathology and it will present the radiologist with a bar chart like that. So that's the pathologies that occurred most often in the top reports that were retrieved for the similarity, for the visual similarity. So you see in this case, lung emphysema and lung nodules occurred very often. This is not a diagnosis, this is just a guide to help the radiologist, a summary of the information. And it doesn't only look in the hospital archives, it can also look further. So, for example, here we have it set up to also look in PubMed to find similar images and also potentially articles about these detected pathologies. And it can also look in, let's say, reference books and find images which could help out. So, of course, this is useful for research, teaching, and clinical work. And it should reduce the 20 minutes to something much less than 5, because all the information is immediately there. Okay, so these have been some examples of the use of medical data to help with clinical decision-making, to help with diagnoses. The problem is very often that it's very difficult to get hold of the medical data, especially even if it is anonymized. So you've heard this a few times during the talk. There's a lot of work to do to actually get this data, and often the people who own the data come up with things like, we can't give you the data because maybe if we give it to you, then your system will be hacked and your data will be, and our data will be stolen. And yeah, they think of all sorts of things why it shouldn't be done. This is why it's also good that many people who think along the ethics of medicine are now thinking along the lines of, given the evidence of what it's possible to do with all of this data, it's actually unethical not to make it available for these types of analyses. So this was written quite nicely in a book in 2011, saying that we believe it is inefficient and in some cases unethical to store such population-based data without installing mechanisms to allow access and publication in appropriate and useful ways. So once we have the medical ethics people on our side, maybe it will move faster and we'll be able to get the data that's needed to do these very useful things. So thank you.